Hey everyone, welcome back to another exciting calculus video because I know we eat, breathe, live math. Yeah. Anyways, this is the warm-up for lesson 4.09. In this lesson, we're going to talk about interpreting derivatives, something that we've done a lot of throughout the entire course. But we're going to kind of solidify things and make sure that we understand them in a more complete way. But before we do that, let's go ahead and get started with the warm-ups. In number one, it's a relatively simple concept to understand. It says, how many extrema does f of x have if f of x is equal to 3x squared times sine of x? And it's giving us an interval -7 less than x less than 7. So we're looking for relative extrema. It's easy enough, it's a calculator-based problem, so it's easy enough to graph this function and just look for where you have high points and where you have low points and say, that's how many relative extrema I have. But this is calculus, and so we want to be able to interpret what we're looking for in light of the derivative. Any kind of justification on the AP exam should be related to something that's calculus-based. And so if we're looking for relative extrema on a function, we have to remember that relative extrema occur, possible candidates occur, when we have critical points. So we have to figure out when the derivative is equal to 0, when the derivative does not exist, and any endpoints that we have. So the first thing I'm going to do is take the derivative of this function. So we'd say f prime of x is equal to, now we're going to have to use the product rule here. So the derivative of the first piece is 6x, and then times the second piece, plus the derivative of the second piece, so the derivative of sine of x is cosine of x, times the first piece. And again, you want to be careful here. We're not multiplying the x times 3x squared. We're multiplying the result of cosine of x times 3x squared. So I'm going to go ahead and write that. I'm going to rewrite it so it's easy to see here. So we're going to say 6x times sine of x plus 3x squared times cosine of x. So we have our derivative here. We're looking for relative extrema. Ultimately, a relative extrema, by definition, occurs when f changes direction. On a continuous function, okay, then f would have to change directions, or at endpoints. Well, in order for a function to change directions, the derivative has to change signs. So if I'm looking for the actual values of where there's an extrema, what x values produce that, I would then set this equal to 0, and then I would solve that, or I would solve that using my calculator. I'd set that equal to 0. I'd graph that function and find the zeros and find all those candidates. But I just want to know how many extrema I have. So I would say something like this. Relative extrema occur when f prime changes signs. And this is a true statement as long as the function is a continuous function. Now we can see that 3x squared times sine of x is in fact a continuous function. So we're looking for when f prime changes signs. So if we looked at the graph of f prime, now we're going to look at our calculator's graph, and we're going to note that we're only going from -7 to 7. And so the graph starts high, it goes down, and then back up, and then back down, just like this. Okay, so it's an even function because it reflects along the y equals x. So that's the graph that you observe on your calculator. Now, the first thing I note is that we have an open interval here. So on an open interval, the endpoints cannot be extrema because those points technically don't exist. So we are looking for when f prime changes signs. We can see that f prime changes signs at this point, this point, this point, and this point here. If we were to do a number line of f prime, it would look something like this. So we'd have -7 as some sort of endpoint. We'd have this point here, whatever that value is, this one. We'd have 0. We'd have this point, and then again 7 at the end. So 7 and negative 7. And these are all zeros for f prime. And then just observing the graph here, we can see that f prime is positive in between negative 7 and that first 0. It's negative in this interval, positive in this interval, and again positive in this interval, and then negative here and positive here. So we can see that there was actually no sign change when x equals 0. We can see that f prime remains above the x-axis. So there is no relative extrema for f at 0 because f prime doesn't change signs there. So we can see that we have 1, 2, 3, 4 relative extrema, over the interval negative 7 to 7 for the graph of f. And again, if I was looking for the actual x values where those extrema occur, I would set this equal to 0. I would find the zeros using my calculator. I'd find these exact points here, and I check for a sign change. And I can see that there's a sign change here, 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 and here. But I'm just asking for how many. All right, for number 2 is a bit worrying, but it's dealing with a concept that we should be kind of comfortable with by now. And I like these types of problems because it's just dealing with the idea of a table and interpreting our information based on tabular data, and it's kind of nice. Now, in this problem, it says f is continuous over the closed interval 1 to 5. So let me write that down. It's continuous for the closed interval 1 to 5. And then it says it's twice differentiable for the open interval 1 to 5. Now, immediately, when I see that a function is continuous over a closed interval and differentiable over an open interval, I'm immediately thinking the mean value theorem here, based on that bit of information. Now, it also tells us that f prime of 3 is equal to negative 1, and that f double prime of x is greater than 0 for every value in this, for every x value within this interval. Okay. Then it also tells us, it gives us a table here of values, or at least one value, of f of x. And then it leaves us blanks for when x equals 1 and x equals 5. So what we need to do is interpret this in light of the fact that the mean value theorem applies. Okay? So what I'm going to do is I'm going to add another part of this table, and I'm going to look at f prime of x here. Okay? Now it told us that f prime of 3 is negative 1, so we can fill that data in. Now here, so we've used that here. Now here it's telling us that f double prime is greater than 0. Well, if we look at our table or our chart, trying to understand what f double prime does for us, f double prime being positive tells us that f is going to be concave up, and it also tells us that f prime is going to be increasing. So since I'm looking at a data table, I can't really observe concavity very easily. So I want to ignore the idea of f being concave up, and I want to focus on the idea of f prime increasing. So I'm going to, based on this statement, I'm going to say, therefore, f prime of x is increasing. Okay? So since f double prime is positive, f prime is increasing. So remember that if I'm looking at the derivative of a function, that implies it's the slope of the curve. And this is where the mean value theorem comes into play. The mean value theorem, if you remember, says that the average slope between 2 points will be equal to the derivative for some value between those 2 points. So if I can find the average slope between x equals 1 and x equals 3, then I know the derivative for some value between 1 and 3. Wherever that is, it's somewhere between 1 and 3. Well, the first thing I know is that f prime is increasing. That means that the slope for for some value between 1 and 3, so I'm going to put a little arrow here, the slope between 1 and 3 has to be such that f prime is increasing, or the slope is increasing. Since the slope is -1 here, the slope before it must be less than -1. Because if the slope is greater than -1, then we would see that the slope is decreasing. We don't want that. Okay? Then the second part of this is the slope between 3 and 5. Well, again, since the slope at 3 is -1, that means the slope after 3 must be greater than -1 for f prime to be increasing. Okay? So we're looking for values for 1 such that the derivative is less than -1, and a value for x equals 5 such that the derivative is greater than -1. So I'm going to go ahead and call this point, whatever this value is, well, I'll call it what it is. It's f of 1. So I'm going to go ahead and find the slope between these 2 points here. So I would say that 10 minus f of 1 over 3 minus 1 must be less than -1. So we're looking for when the slope is less than -1. Now we can work this out. We can say 10 minus f of 1 over 2 is less than -1. Then we cross multiply, so 10 minus f of 1 is greater than -2. We'll subtract the 10, so f of 1 is less than -12. And then as a result, we've got to flip that inequality, divide by -1. So f of 1 must be greater than 12. Okay? So we know that this value must be greater than 12. Sorry about all these little arrows and inequality ideas here. But thinking through that again to make sure we understand that, if it was equal to 12, if I found the slope between these 2 points, then I would have a drop of 2 and a rise of 2. So that would give me a slope of -1 in between these 2 points. The slope would be -1 if this was 12. It can't be -1 because I need to see f prime increasing here. And it wouldn't be, it would be -1 exactly. So we know that this guy has to be a value greater than 12. We can conclude then that f of 1, well, I just wrote it down here. F of 1 must be greater than 12. Okay? Now for the last part, for f of 5, we know that the slope between 3 and 5 must be greater than -1. So we would say f of 5 minus 10 over 5 minus 3 must be greater than -1. And then we can solve this. This is just light work, I guess you could say. So we'll multiply by 2 there. So we got f of 5 minus 10 is greater than -2. And then we'll add the 10. So f of 5 is greater than 8. So again, let's assume for a second that f of 5 is equal to 8. Well, if f of 5 was equal to 8, then the slope from 3 to 5 would be a drop of 2 and an increase of 2. So the slope between these 2 points would be -1 exactly. But we need the slope to be greater than -1, not equal to -1. And the reason being is because we need to see a progression here. We need to see that f prime is increasing. So we should see values of f prime that are less than -1 before x equals 3 and greater than -1 for x values greater than 3. So this must be true for both of these in order for f double prime to be greater than 0. I hope that kind of warms your mind up a little bit to our next lesson. So go ahead and stick around and watch the next lesson. Of course, I think calculus is exciting no matter what, but hey, you might find something out of it.